Hello, and thank you for coming to listen to my talk about transport dynamics of microparticles in inertial elastic vortex flows. My name is Noah Bolton, and I'm a postdoc with Professor Anka Lindner at ESPCI Paris. And this work is done with collaboration with Professor Luca Brandt and Alash Banai from KTH Stockholm, and also with Professor Amy Shen and Dr. Simon Howard from Okinawa, Japan. And in order to study particle flow in a single vortical flow field, first we need to generate this type of flow field. And we do this by using the cross-law geometry, where we have inflow from two opposing directions and outflow from the other two opposing directions. This induces a flow instability upon a critical Reynolds number, which results in a vortex formation that is stretched downstream. If we take a slice or a cross-section from this flow field, we can plot the streamlines and see how this flow behaves, and we can recognize a stagnation point at the center of the flow field. We have conducted both experiments and numerical simulations adding neutrally buoyant particles to the flow field. From the simulations, we can capture the three-dimensional flow field. So here we are simulating 140 micrometer particles. And from the experiments, we can have a two-dimensional look of the flow field at exactly the cross-section of the vortex flow, so the very center plane. From both experiments and simulations, we can then extract the particle positions and reconstruct their trajectories, and we can see how nicely the simulations agree with the experiments, showing that no particles can enter the center of the vertical flow field. But if we look at smaller particles, we can see that they do enter the center of the vortex. If we want to understand this better, we can directly compare a streamline and a trajectory of a large particle. So we can consider the streamline as a small particle will follow exactly the path of the streamline, being affected from only one streamline. But once we have a large particle, it will be affected from the three-dimensionality of the flow field, so from several streamlines, and will be transported out of the center plane at an earlier point than the smaller particle. But how can we further control particle position in a vertical flow field? So in order to study this, we have added elasticity to the fluid. We used polyethylene oxide solution with a high molecular weight and a dilute concentration. And we see the dramatic effect of the elasticity on the particle positions in the flow field. We can explain this by looking at numerical simulations and plotting the first normal stress difference that tells us where exactly the polymers stretch in the flow field. We see that the high polymer torque can act both counter to the vorticity and also cause an expulsion of particles from the center of the vortex. If you would like to hear more details, please listen to our longer presentation, and we'll be happy to answer any questions you might have. Thank you.